Machine learning and AI agents. Machine learning (ML) is a cornerstone of modern AI agents, enabling them to learn from data and experiences to improve their performance over time. Unlike traditional rule-based systems, which require explicit programming for each task, AI agents that use machine learning can adjust their behaviors autonomously based on the input they receive. This ability to learn is essential for agents to adapt to new environments, improve decision-making, and optimize their actions. The learning process can take many forms, depending on the type of machine learning algorithm being applied. Understanding these different learning mechanisms is key to appreciating how AI agents become more intelligent and efficient in real-world tasks. How AI agents learn: supervised, unsupervised, and reinforcement learning. AI agents typically learn using one of three primary methods: supervised learning, unsupervised learning, or reinforcement learning. Each method has its own strengths and applications, and the choice of which to use depends on the problem the agent is solving and the type of data available. 1. Supervised learning. Supervised learning is one of the most common methods used in AI agents. In this method, the agent is trained on labeled data, meaning that each input is paired with a known output. The goal of the agent is to learn the relationship between the inputs and the outputs, so it can accurately predict outcomes for new, unseen inputs. For instance, a chatbot trained to understand customer queries might be trained on a large dataset of questions paired with appropriate answers. During the training phase, the agent makes predictions and compares them with the actual output. It then adjusts its internal model to minimize the error between its prediction and the actual result. Over time, as the agent sees more data, it improves its accuracy. Supervised learning is particularly useful in tasks where the correct answers are well defined, such as image recognition, spam detection, or natural language processing. 2. Unsupervised learning. In contrast to supervised learning, unsupervised learning involves training an AI agent on data that does not have explicit labels. The agent must learn patterns, structures, or relationships in the data without knowing the correct outputs in advance. This method is often used for clustering or grouping similar items together or detecting anomalies in data. For example, an unsupervised learning agent might analyze customer behavior data and group customers into segments based on their buying habits, even though it doesn't know the specifics of each customer's identity. Unsupervised learning is valuable when dealing with large datasets where labels are unavailable or costly to obtain. It allows agents to discover hidden patterns in data that might not be obvious to human analysts. 3. Reinforcement learning. Reinforcement learning, RL, is a powerful learning technique that allows AI agents to learn by interacting with their environment and receiving feedback in the form of rewards or penalties. In this framework, the agent learns by trial and error, continually refining its actions to maximize cumulative rewards over time. Unlike supervised learning, where the correct answer is provided up front, reinforcement learning relies on the agent's exploration of the environment and the consequences of its actions to learn. One classic example of reinforcement learning is training a robot to navigate a maze. The robot receives positive rewards for moving closer to the exit and penalties for bumping into walls. Over time, it learns which actions are most likely to lead it to the goal. Reinforcement learning is particularly well suited for tasks where agents must make sequential decisions, such as in robotics, game playing, or autonomous driving. Neural networks and deep learning in AI agents. At the heart of many AI agents' ability to learn are neural networks, which are computational models inspired by the structure and function of the human brain. These networks consist of layers of interconnected nodes, or neurons, that process input data and produce outputs. The connections between the nodes are weighted, and these weights are adjusted during the learning process to improve the network's predictions or decisions. Deep learning, a subset of machine learning, involves the use of neural networks with many layers, hence the term deep. Deep learning models have revolutionized AI, particularly in areas such as image and speech recognition, where they have achieved unprecedented levels of accuracy. By stacking multiple layers, deep neural networks can learn increasingly complex representations of the data, allowing them to tackle tasks that were previously too challenging for traditional machine learning models. For example, in a deep learning powered AI agent designed for autonomous driving, the neural network might consist of multiple layers that process raw camera images from the car. The early layers might detect simple features, such as edges or corners, while the deeper layers could recognize more complex patterns like pedestrians, traffic signs, or other vehicles. Deep learning has proven to be especially effective in AI agents that need to process vast amounts of unstructured data, such as images, audio, or text. It has also enabled the development of generative AI, where agents can not only analyze data, but also create new content, such as generating text, music, or even artwork. The success of deep learning is largely due to the availability of large datasets and powerful computing resources that allow these complex models to be trained. However, one challenge with neural networks, especially deep learning models, is their black box nature. While they can achieve high accuracy, it's often difficult to interpret how or why a particular decision was made, raising concerns about transparency and accountability in critical applications like healthcare or finance. In conclusion, machine learning is a fundamental aspect of how AI agents function and improve their performance over time. Through supervised, unsupervised, and reinforcement learning, agents can adapt to their environments, make better decisions, and continuously refine their strategies. Neural networks, especially in the form of deep learning, have further enhanced the capabilities of AI agents, enabling them to tackle complex tasks in a variety of fields. As these technologies continue to evolve, AI agents will become increasingly sophisticated, learning more efficiently, and solving even more complex problems across industries.